Picture a quiet control room, a few tired people, and a spectrum of Barnard's star scrolling onto the screen like it had 1,000 times before. This was supposed to be routine. Point the most powerful telescope ever built at a small red star, collect the light, log the data, move on. Then one line in that reading refused to behave. Nobody spoke for a moment. The kind of silence you get when trained people are quietly hoping they misread something. That's the story here, and it starts with a single measurement that didn't match what anyone expected from a star we thought we understood. I'm not going to hand you the answer yet, because the answer only lands once you understand the setup. To understand why a single line of data rattled seasoned astronomers, you have to know how absurdly close this star sits. Barnard's star is about 6 light-years away. In cosmic terms, that's next door. Only the Alpha Centauri system sits closer, which makes this faint red dwarf the nearest single star to our Sun. 6 light-years still sounds impossibly far, and it is. But out of hundreds of billions of stars in the galaxy, you can count the ones nearer than this on one hand. When something turns up at a place this close, it stops feeling like a distant curiosity and starts feeling like it's in our own backyard. That proximity is exactly why astronomers keep coming back to it, decade after decade, watching, measuring, checking. So when Webb turned its instruments this way, expectations were low and familiar. The people watching the screen had spent careers being careful, which is why their reaction meant something. These aren't people who gasp at data. They double-check, they run it again, they assume the boring explanation first. Careers are built on not overreacting to a strange line on a graph. But something about this reading held them there longer than it should have. One person leaned in, another pulled up the raw file. The easy conversation in the room just stopped, replaced by that focused, uncomfortable quiet, where everyone is thinking the same thing, and nobody wants to say it out loud yet. Because saying it out loud would mean taking it seriously, and taking it seriously meant a lot of follow-up work and a lot of ways to look foolish. So they reached for the safest thought available. Their first instinct was the obvious one. The machine had made a mistake. So they checked the machine first, they pulled the calibration files, compared them against known reference stars, and looked for the fingerprints of a detector glitch. Cosmic rays can slam into a sensor and leave a false spike, so they hunted for those too. Then they re-observed. A second pass on a different day, with the instrument reset, should wash out any one-time fluke. If the signal was noise, it would drift or vanish. It didn't. It came back in the same place, the same shape, steady as the first time. One by one, the easy answers fell away. Not a thermal artifact, not a stray reflection inside the optics, not a software rounding error in the pipeline. Every comfortable explanation got crossed off the list, and something was still sitting there in the data, refusing to leave. To grasp the full weight of it, we have to rewind more than 2 centuries. Go back before Webb, before the giant ground telescopes, before anyone had photographed a single star. For most of human history, this object wasn't even a point of light people could see. It's far too faint for the naked eye, hiding in a patch of sky in the constellation Ophiuchus. The tools had to catch up to the target. First the telescope, then the camera, then the ability to measure a star's motion across the sky year after year. Each new instrument peeled back a little more, turning a smudge on a glass plate into a world we could actually study. It took generations of patient watchers to even notice this thing was special, and the closer they looked, the stranger it got. This is a story astronomers have been getting wrong, spectacularly, for over 100 years. Here's what Webb actually changes. We thought we had this star figured out. We'd catalogued its size, its color, its age, its temperature, and slotted it neatly into the story of how stars like it live and die. What the telescope pulled back doesn't fit that tidy picture. It touches how we search for planets, how we judge which stars could hold life, and how confident we should really be about the objects sitting right next door to us. A single reading forced people to reopen questions they'd considered closed. But to understand why one faint smudge could rattle so many assumptions, you have to know what makes it unique in the first place. It starts with why this particular ember matters more than almost any other in the sky. Barnard's star sits about 5.96 light-years away, which makes it the closest single star to our Sun. Only the Alpha Centauri system, a trio of stars, sits nearer. That proximity turns it into something rare, a target close enough that our instruments can actually resolve fine detail instead of guessing from a blur. For planet hunters, distance is everything. The closer a star, the easier it is to catch the tiny wobble a planet's gravity drags it through, and the sharper any faint companion appears. A world orbiting Barnard's star would be one of the most studyable planets outside our own system, close enough to imagine following up for decades. So astronomers have watched it for over a century, measuring its light, tracking its motion, listening for the faintest tug. It's the kind of star you'd expect to have given up its secrets long ago. For most of history, everyone assumed there was nothing remarkable here at all. The picture we built was almost boring. A small red dwarf, roughly 16% the mass of the Sun, burning so slowly it puts out less than 1% of the Sun's light. Cool, faint, ancient, the kind of star that just sits there and quietly ages for billions of years. Decades of radial velocity measurements came back flat or muddied by the star's own restlessness. Every so often, someone announced a planet, and every time the signal fell apart under closer scrutiny. The famous 2018 candidate, a supposed frozen super-Earth, was quietly retracted a few years later when better data showed the wobble was the star itself, not a world. So the file stayed closed. Barnard's star was the empty neighbor, useful mainly as a benchmark, a calm reference point in a noisy sky. That assumption would be broken, restored, and broken again more than once. Which brings us back to the reading that started all this. James Webb wasn't built to chase headlines around a dim red dwarf. It was pointed there for careful, routine reasons. And what came back didn't match the calm, settled story anyone expected. The problem wasn't that the data was loud. It was that it was specific, in a way that didn't fit the assumptions people had spent decades hardening into fact. A star this well studied isn't supposed to surprise you, and this one did. That's the question hanging over everything else. How does a place we thought we understood completely hand us something we can't immediately explain? To answer it, you have to go back further than Webb, further than the retracted planets, all the way to the beginning. Before the fear, there was only a photograph and a man who noticed something move. For most of human history, the sky looked fixed. The stars sat where they'd always sat, night after night, generation after generation, like pins driven into a black ceiling that never shifted. People built calendars and religions on that stillness, trusting that what your grandfather saw overhead was exactly what you'd see too. And it was a reasonable thing to believe. The stars are so far away that their motion, if it exists at all, is far too slow for the naked eye to catch across a single lifetime. You could stare up every clear night for 80 years and never notice a single one drift out of place. So it took a very particular kind of person to prove that stillness was an illusion. Not a wealthy astronomer with a private observatory, not a professor born into the field. It took someone who came at the sky sideways, from poverty, with nothing but patience and a hunger, to look closer than anyone around him. That man taught himself the sky before he could afford a telescope. His name was Edward Emerson Barnard, born in Nashville in 1857, into a family with almost nothing. His father had died before he was born, and by age 9 he was working long days in a photography studio, holding a camera steady on a rooftop to track the sun. That job, dull as it sounds, taught him two things that would define his life: how to handle a lens and how to sit still and watch. He couldn't afford formal schooling, so he read what he could and taught himself the constellations by eye. He saved for years to buy a modest 5-inch telescope, then started hunting comets from his own backyard. He found them, one after another, and small cash prizes for each discovery slowly funded his obsession. By the time real observatories noticed him, he'd already become one of the sharpest visual observers alive, a man who could pull detail out of the sky that trained scientists missed. He landed at Lick Observatory, then Yerkes, working with some of the finest instruments in the world. In 1916, a pair of photographic plates showed him something no star was supposed to do. The trick Barnard used was simple in idea and brutal in practice. You photograph the same patch of sky, then wait years and photograph it again from the exact same setup. Lay the two plates side by side, and almost everything lines up perfectly. Almost. When he compared images of one faint star in the constellation Ophiuchus, taken years apart, it hadn't stayed put. It had crept across the frame, a tiny but unmistakable shift against the fixed background behind it. To the eye, it was nothing, a hair's width on a glass plate. To an astronomer, it was enormous. He measured the movement at about 10.3 arcseconds per year, a rate that meant this dim little star was tearing across our sky faster than any other ever recorded. No star in the sky moves faster than this one, and that fact alone changed everything. To put that in perspective, most stars in our sky barely budge over a human lifetime. Their positions shift so little that ancient sky maps still line up with what we see tonight. Barnard's star breaks that rule completely. In just 180 years, it drifts across a patch of sky about the width of the full moon. Watch it long enough, and you can literally see it march against the fixed backdrop of more distant stars. Nothing else we've catalogued moves like this. That record has held for over a century now. Astronomers even nicknamed it Barnard's runaway star because it seems to be in a hurry to get somewhere. That speed was not a curiosity, it was a clue about where the star came from. The kind of motion we're talking about has a name. Astronomers call it proper motion, and it just means how fast a star appears to slide across the sky from our point of view. It's measured in arcseconds, tiny slivers of an angle where a single degree holds 3,600 of them. Here's what makes Barnard's star special. A star can be racing through space at incredible speed, but if it's far away, that motion looks frozen from Earth. Nearness is what amplifies the effect, the same way a car on a distant highway crawls while one right beside you flashes past. So a large proper motion usually points to a close neighbor. Barnard's star sits just under 6 light-years away, which is part of why it appears to move so dramatically. For all that motion, you could stand outside on the clearest night and never see it. That's because Barnard's star is a red dwarf, one of the smallest and faintest kinds of star that exist. It glows at roughly magnitude 9.5, well below the limit of human vision, which cuts off around magnitude 6. Even at its close distance, its light is simply too weak to reach your eyes unaided. You'd need a decent pair of binoculars or a small telescope just to spot it as a faint reddish point. It puts out only a tiny fraction of the light our sun does, and most of what it emits leaks out as infrared, heat rather than visible glow. It's less a beacon and more a smoldering coal in the dark. A star this dim, this small, this cool, burns its fuel at a crawl. Everything about it, its size, its cold light, pointed to something far older than our sun. Let's put numbers on it. Barnard's star holds roughly 16% the mass of our sun and about 19% its width. If you dropped it where the sun sits, it would be a little bigger than Jupiter, a red bulb hanging in a sky gone dark. Its surface simmers near 3,100 Kelvin, barely half the heat of our own star. That cool skin is why it glows red instead of white, and why almost all its light leaks out as infrared we can't even see with our eyes. A star this light doesn't roar through its hydrogen, it sips it, slow and steady, stretching a single tank of fuel across spans of time that dwarf the age of everything you know. This is one of the oldest stars we can reach, and its age hides a threat. When astronomers ran the numbers, they landed on a figure that's hard to hold in your head. Barnard's star is likely somewhere around 10 billion years old. Our Sun, by comparison, is about 4.6 billion. This little ember predates it by more than twice over. Think about what that means. When Barnard's star first lit up, there was no Earth, no Sun, no solar system at all. The galaxy itself was still young, still assembling, still figuring out what it wanted to be. It has watched generations of brighter stars flare up, burn hard, and die in the time it's quietly kept going. It's a survivor from an era we can only study in fragments. Its ancient chemistry told astronomers it had survived since the galaxy was young. That chemistry leaves a fingerprint. Astronomers measure what they call metallicity, the fraction of a star made from anything heavier than hydrogen and helium. Barnard's star comes back low, poor in those heavier elements compared to the Sun. There's a reason for that. Heavy elements like iron, carbon, and oxygen get forged inside stars and scattered when they die. So the more of them a star carries, the later it must have formed, after earlier generations had time to seed the galaxy. A metal-poor star like this one was built from cleaner, more primitive gas, the stuff of a younger cosmos that hadn't been enriched yet. Everything lined up. A star this close and this old should have been the perfect place to hunt for worlds. Think about how empty space actually is. The nearest star to our Sun sits about 4.2 light-years away in the Alpha Centauri system, 3 suns bound together in a slow gravitational dance. After that trio, nothing else is closer than Barnard's star. It floats roughly 6 light-years out, which sounds impossibly far, and it is. But on the scale of the galaxy, that's next door. Out of every single star we can point to, only one system beats it for proximity, and that one comes as a package of 3. Barnard's star is the closest lone star to us, a single dim sun drifting in the dark just beyond our doorstep. And unlike most neighbors, this one is not staying put. Most stars we map hold their positions across a human lifetime, fixed points we can trust. Barnard's star doesn't. It's moving toward us, closing the gap between its position and ours a little more every year. Run the math forward and the numbers get strange. In roughly 11,000 years, it will reach its closest approach to the Sun, pulling in to about 3.75 light-years. For a while, it will become the nearest star to us, edging out even the Alpha Centauri system. At the time this was first understood, that fact was little more than a curiosity, a line in a catalogue, a wandering star, drifting closer, then eventually pulling away again into the deep. Astronomers noted it and moved on to what actually held their attention. The real question was never where it was going, but what might be circling it. Barnard's star is a red dwarf, and for a long time that word carried a promise of calm. It burns through its hydrogen slowly, sipping fuel instead of gulping it, which is exactly why a star this small can keep glowing for tens of billions of years. No violent swelling, no rapid changes, just a steady, low ember holding constant across timescales that dwarf the age of the Sun. To early astronomers, that made it sound like an ideal host, a quiet, patient star, the kind of place where a planet could settle into a stable orbit and simply stay there, undisturbed. So the assumption formed easily. If worlds existed around Barnard's star, they'd be circling a gentle, predictable sun. That picture felt safe, and it shaped how people expected the search to go. To answer whether planets existed, someone had to measure a movement almost too small to see. Here's the thing. A planet never sits still, and neither does its star. Gravity works both ways. A world in orbit pulls on the star that holds it, and the star answers with a tiny circle of its own around their shared center of mass. For something like Jupiter tugging on a distant sun, that motion is almost nothing. We're talking a shift of a fraction of a second of arc, roughly the width of a coin seen from kilometers away. Yet if you could catch it, you'd have proof of a planet you could never see directly. That was the promise hiding inside Barnard's star. If a giant world circled it, the star would trace a faint scallop across the sky, a wiggle laid over its fast, straight march. There was a technique for catching that tug, and it demanded almost inhuman patience. The method was called astrometry, and the idea is simple, even if the work isn't. You photograph a star, then photograph it again years later, then again, and you measure exactly where it lands against the fixed background stars each time. Every image was a glass photographic plate, and the star's position got measured against reference stars down to microns on the emulsion. A wobble wouldn't show up in one plate, or 10. It might only emerge after hundreds of exposures, spread across decades, each one compared against the last with painstaking care. Barnard's star was the ideal target for this. It's close, it moves fast, and any planetary tug would be larger and easier to spot than around a more distant sun. Finding planets next door would hand us the nearest worlds we could ever hope to study. Think about what that would have meant in the mid-20th century. No one had confirmed a single planet beyond our own solar system. The idea that other stars carried worlds was an assumption, a hope, something people believed but couldn't prove. And here was a star just 6 light-years out, the second closest system to the Sun, close enough that its planets might actually leave a fingerprint we could measure. A detection here wouldn't just be one more data point. It would be the first, the opening of a door humanity had stared at for centuries. Barnard's star sat right on our cosmic doorstep, brighter in infrared than in visible light, waiting. Nearby meant reachable, at least in imagination, and that made the prize irresistible. Think about what a planet at 6 light-years would actually mean. Every other world we might hope to study sits tens or hundreds of light-years away, faint smudges lost in the glare of their stars. A planet circling Barnard's star would be close enough to measure, close enough to dream about, close enough that its light might one day reach a telescope built to read it. Distance is everything in this game. The closer a system, the larger the angle its planet sweeps across the sky, and the easier it becomes to catch that tiny motion. A world next door wouldn't just be a data point. It would be the test case, the one nearby laboratory for asking whether planets form around stars nothing like our Sun. So the stakes were enormous. Find a planet here, and you'd prove that worlds were common, that our solar system wasn't a fluke. You'd hand the next century a target it could actually visit in thought and equations. But the tools of the era were photographic plates and human patience. Picture the astronomy of the early 1900s. No digital sensors, no computers humming in a control room. A telescope pointed at the sky, and behind it, a glass plate coated in light-sensitive emulsion, exposed for minutes at a time until the stars burned themselves into the chemistry. Each plate was developed by hand in a darkroom, then stored in a paper sleeve and filed away. Measuring a star's position meant sliding that plate under a machine and reading the coordinates off finely ruled screws, squinting through a microscope, jotting numbers in a ledger. The precision came from craftsmanship, from steady hands repeating the same careful ritual thousands of times. It was slow, beautiful, painstaking work. To track a star's motion, you needed decades of plates, taken with the same instrument, under the same conditions, compared point by point. One observatory and one astronomer would stake everything on watching this single star. Patience wasn't a virtue here. It was the entire method. A planet tugging on its star produces a wobble so small it hides beneath years of ordinary motion, and the only way to see it is to keep looking, season after season, until the pattern separates itself from the noise. So you return to the same star, the same telescope, the same slice of sky, again and again. You wait for the weather, for the star to climb high enough, for the night to be dark and steady. A single year tells you almost nothing. 10 years begins to whisper. 20 or 30 years might finally speak. It's the kind of work that outlasts careers and consumes them whole, a quiet accumulation of glass and numbers stretching across a lifetime. Somewhere in that long patience, an answer was supposed to emerge. That astronomer had a name, and for a while it would be famous. His name was Peter van der Kamp, and he was born in the Netherlands in 1901, back when photographic astronomy was still young, and half the sky felt unmeasured. He crossed the Atlantic in the 1920s, chasing a discipline that rewarded people who could sit still for years. By the time he settled into his career, he'd already learned the trick that would carry him. You don't hunt the sky all at once, you pick one point of light and refuse to let go. Colleagues remembered him as precise, patient, almost gentle with his instruments. He wasn't the kind of scientist who chased headlines or big surveys. He wanted depth, not breadth. One target followed so closely that its smallest motion became familiar. And of all the stars he could have chosen, he settled on the fast little red one Edward Barnard had catalogued years before. He would devote most of his life to one faint red star, and it would define him. The choice made a kind of sense. Barnard's star sits under 6 light-years away, one of the closest neighbors we have, and it races across the sky faster than any other star we know. That speed matters, because a nearby, fast-moving star is exactly where a hidden planet's tug would be easiest to see. If something massive orbited it, the star wouldn't travel in a clean, straight line. It would trace a faint wave, drifting slightly off course, and then back again, over and over. Van der Kamp knew that a wobble that small would take years to confirm, maybe decades, and he was willing to spend them. So he committed, not to a season of observing, not to a grant cycle, but to the long haul, measuring the same star again and again while the world changed around him. His work happened at one small observatory, plate by patient plate. That observatory was Sproul, tucked onto the campus of Swarthmore College in Pennsylvania. Its centerpiece was a 24-inch refractor, an older design built for exactly this kind of slow, careful star position work. Van der Kamp became its director in 1937 and stayed for decades, turning a modest teaching telescope into a machine built around a single question. The method was glass and light. Each night, the telescope exposed a photographic plate, freezing the star and its neighbors in silver grains, and each plate had to be measured by hand under a microscope. You compared the star's position against the fixed background, night after night, year after year, hunting for a shift finer than a hair. Sproul's archive grew into one of the deepest records of Barnard's star anywhere on Earth, stretching back across the years like tree rings. Thousands of exposures piled up, each one a chance to catch the wobble. By the time the collection matured, it held thousands of glass photographic plates, each one recording Barnard's star and the faint field of reference stars around it. Some plates went back to 1916, long before Van der Kamp ever touched the telescope. That kind of baseline is rare. The longer your timeline, the smaller the motion you can tease out of the noise. He measured those plates by hand, using a machine that could read a star's position down to microns on the glass. A single exposure meant nothing on its own. The power was in the pile. Tens of thousands of measurements stacked across roughly half a century, averaged and cross-checked until a pattern might rise out of the scatter. It was slow, exacting work, the sort that rewards a person who can stare at the same star for a lifetime and not blink. And as the years of data accumulated, Van der Kamp began to notice something in the path Barnard's star traced across the sky. Somewhere in that mountain of data, he was sure he saw the star wiggle. A star's proper motion should be a clean, straight line drifting across the background. Barnard's star didn't quite behave. When Van der Kamp plotted its position over decades, the track seemed to sway ever so slightly from side to side, a gentle curve laid over the straight-line march. The size of the shift was almost nothing, a few thousandths of an arcsecond, far finer than the width of the star's own image on the plate. But it appeared to repeat. The star seemed to lean one way, then drift back, then lean again, on a rhythm measured in decades rather than nights. To him, that rhythm had only one natural explanation. Something unseen was tugging the star, pulling it back and forth around a shared center of mass, the same way an orbiting body pulls on the thing it circles. He checked and rechecked, and the wiggle held. In 1963, he told the world what that wiggle meant. Peter van der Kamp announced that Barnard's star, that dim red neighbor just 6 light-years away, was being pulled by an unseen companion. Not another star, not a faint dwarf hiding in the glare, something smaller, something planetary. From the size of the wiggle and the star's distance, he worked out the mass of whatever was doing the pulling. His numbers pointed to a body a bit heavier than Jupiter, swinging around the star on a wide orbit of roughly 24 years. This was a claim no one had ever been able to make with confidence about any star but our own. For the first time, a scientist stood up with decades of data and pointed at another sun and said a planet is orbiting there. He said a giant world, something like Jupiter, was hiding right next door. The world Peter van der Kamp described wasn't small or subtle. He put its mass at roughly 1.6 times Jupiter's, a heavyweight circling Barnard's star once every 24 years. And it sat almost impossibly close to home, just 6 light-years out, in the second nearest star system to our own. Think about what that meant to anyone reading it. The closest single star to the Sun, and it might come with a giant planet already attached. Not a faint smudge halfway across the galaxy, but a neighbor, close enough that future generations might actually study it, map it, maybe even reach toward it someday. It was the kind of finding that rewrote what felt possible. Planets weren't just a lucky accident that happened here. They might be scattered all around us, waiting on the doorstep. The reaction was immediate, and it was not skepticism. The news moved fast for its era. Van der Kamp's result landed in respected journals, and it carried the weight of a man who'd spent decades bent over photographic plates. This wasn't a wild guess from a newcomer. It was the careful conclusion of an established astronomer at a serious observatory. Colleagues took it seriously. Newspapers ran with it. For the public, here was a name they could point to, Barnard's star, and a fact they could hold on to. It had a planet. The discovery gave people a concrete answer to a question humans had asked forever. And van der Kamp became the man who found it. He lectured on it, defended it, built a reputation around it. The claim didn't just survive the first wave of attention, it grew stronger with each retelling. It was so accepted that it started showing up in the places we teach from. Astronomy textbooks began citing Barnard's star as the first solid case of a planet beyond our sun. Popular science books repeated it. Students learned it as settled fact, the way you'd learn that Jupiter has moons. A whole generation absorbed the idea that the nearest planetary neighbor had already been found. It became a fixed point. Writers used it to argue that planets must be common, that the galaxy was probably full of them. The Barnard star planet did real work in shaping how people imagined the universe, all resting on those tiny shifts van der Kamp had measured on glass. The story had everything it needed to stick: a patient scientist, a lifetime of data, a world next door. Then van der Kamp went further and said there was not one planet, but 2. By 1969, van der Kamp had reworked his whole model. One companion couldn't explain the way the star wandered across his plates, so he split the signal in 2. One planet at about 1.1 Jupiter masses, another near 0.8, tracing orbits of roughly 26 and 12 years. It was an elegant fix, 2 worlds pulling on the star from different distances, each tugging in its own rhythm, together producing the wobble he'd measured for decades. On paper, it accounted for every bend in the line. What he didn't publish was how uneven those measurements really were. Some plates disagreed with others by amounts that should have made him pause. He kept the tidy conclusion and left the messier parts out of the spotlight. The curve he drew from the plates looked almost too clean. Look closely at that curve and you can see why it convinced people. It rose and fell in smooth, repeating waves, the kind of periodic signal you'd expect from real planets on real orbits. each cycle lined up with the next like clockwork. Real astrometric data almost never looks that neat. You're measuring shifts smaller than 1/100th of a pixel on photographic glass, across thousands of exposures taken over 40 years. Dust, temperature, and human hands all leave fingerprints on numbers that fine. So a signal this smooth wasn't just impressive, it was the kind of thing that should have raised a question about where the smoothness actually came from. A few researchers started asking it quietly. For years, the applause drowned out the quieter voices at the back of the room. And there was a lot of applause. Van der Kamp was the man who'd found planets around another star, decades before anyone had the tools to confirm one. He lectured to packed halls, his name attached to one of the great discoveries of the century. Barnard's star became his star. Colleagues cited his measurements as the gold standard for what patient astrometry could achieve. Students trained on his methods, and the two-planet system moved from a claim into something close to settled fact. For a man who'd spent his life squinting at glass plates, this was the summit. The data had spoken, the world had listened, and the wobble looked permanent. But when others ran the numbers, something refused to add up. The trouble started quietly, the way real trouble usually does. A few astronomers who had no stake in the discovery pulled Van der Kamp's numbers and started checking his math. And the deeper they went, the stranger it felt. The planetary signal was there, sure, but it behaved in a way that nagged at them. Real orbits are messy. A planet tugging on a star leaves a signature shaped by gravity, and gravity doesn't care about being neat. Yet this wobble came back on schedule, clean and repeating, almost like it had been drawn with a ruler instead of measured off the sky. That's what unsettled them, not that the signal was weak, but that it was smooth in a way stellar motion almost never is. The wobble was almost suspiciously tidy, and tidy is rarely how nature behaves. So they looked harder at the shape of it. When a planet orbits a star, the star traces a slow, looping path, and that path wobbles with the planet's pull, but it also carries the noise of a real physical object moving through space. There should be scatter, jitter, small imperfections that never fully cancel out. This signal had almost none of that. It rose and fell with a regularity that felt mechanical, like a metronome rather than a moon. The more precisely they mapped it, the more it resembled a pattern imposed on the data instead of one pulled out of it. And once you notice that, you can't unsee it. A wobble that perfect starts to look less like a planet and more like an artifact. A handful of astronomers started asking an uncomfortable question about the telescope itself. At first, saying it out loud felt almost rude. Van der Kamp was respected, decorated, the elder statesman of American astrometry, and his result was already in the textbooks. Publicly doubting him meant doubting decades of careful work by a man most of them admired. But a few pressed anyway. They pointed out that no other observatory had confirmed the wobble, and that the entire claim rested on plates taken by a single instrument in a single place over a single long stretch of time. One dataset, one telescope, one man's life's work. If the planet was real, it should show up elsewhere, on other glass, through other lenses. It hadn't, and that silence pushed the skeptics toward a possibility nobody wanted to voice. So they went looking, not at the star, but at the instrument that had watched it. The team pulled Van der Kamp's original photographic plates out of storage, thousands of glass images stacked across decades. Each one had captured Barnard's star as a tiny point of light, and each had been measured by hand, star against star, to hunt for the faintest sideways drift. That measuring was the whole game. If the star wobbled, the wobble had to show up as a shift of position on the plate. So they rechecked the math, the reference stars, the way the shifts were logged year by year. Everything Van der Kamp had reported was internally consistent. The wobble was real in the data. That was the strange part. The signal existed. The question was whether it came from the sky at all, or from something closer to home. They kept the reinvestigation quiet, because if they were right, they weren't correcting a small error. They were dismantling one of the most celebrated results in the field. The answer was sitting in the lens the whole time. A refracting telescope like the one at Sproul focuses starlight through a big glass objective, and every measurement of position depends on that glass staying exactly the same shape, night after night, year after year. If the lens shifted, if it was cleaned, remounted or realigned, the stars would appear to move ever so slightly across the plates, not because they moved, but because the instrument did. That kind of shift wouldn't look random. It could smear across every star in the frame in a smooth, gentle curve, exactly the kind of slow, elegant swing that looks like a planet tugging on its sun over decades. So the investigators stopped asking what Barnard's star had done and started asking what had been done to the telescope. They went digging through the observatory's maintenance logs. The telescope had been serviced, and the dates would prove devastating. The records were mundane, the sort of housekeeping every big instrument goes through. In the late 1940s, the objective lens had been removed and reworked. Then again in the 1950s, the optics were adjusted a second time. Routine care for a hard-working telescope, logged and forgotten. On their own, those entries meant nothing. A lens gets cleaned, a mount gets tightened. Nobody writes it down expecting it to rewrite a discovery 2 decades later. But Van de Kamp's wobble wasn't one smooth swing. It had kinks in it, moments where the star's supposed path seemed to jump or change direction. So the team took the timeline of those position jumps and laid it over the dates the lens had been touched. When they lined the wobble up against those service dates, the coincidence was chilling. Every time the wobble took a sharp turn, a technician had just been at the telescope. In 1949, the lens was removed, cleaned, and reseated, and the star's path bent right there. In 1957, new equipment went in, and the path bent again. The star wasn't drawing a planet's signature across the sky. It was tracing the maintenance schedule of an observatory in Pennsylvania. Think about what that means. For years, the smoothest, most convincing part of the data, the gentle curve everyone trusted, was moving in step with a wrench and a screwdriver. The planet's orbit and the repair log kept the same calendar. You can imagine the room going quiet as that overlay came up. The gaps between position jumps didn't match any orbit. They matched the days people had opened up the instrument and touched it, which forced a conclusion no one wanted to say out loud. If the jumps line up with the hardware and not with anything in the sky, the source isn't 6 light-years away. It's in the tube. The wobble was the telescope shifting its own reference frame every time the optics were disturbed, then holding that new position until the next adjustment nudged it again. That's the moment the whole thing inverts. The signal that had been read as a distant world was really a record of the machine measuring itself. Barnard's star had sat there, steady, indifferent, while the instrument below it drifted and jerked and wrote a fiction into the plates. So the answer everyone had been circling finally settled. The tiny motions weren't gravity. They weren't a companion tugging on a star. They were an artifact, born inside the equipment that was supposed to be watching. The planets Van de Kamp had spent his life on had never been there. By the early 1970s, other astronomers were pointing their own telescopes at Barnard's star, and they saw nothing. No wobble, no companion, no matching curve. When the star was measured by instruments that hadn't been taken apart and reassembled, it simply held still. The verdict was the harder kind, the kind that leaves nothing behind. There was no faint planet waiting to be confirmed with a better lens. There was no smaller signal hiding under the false one. The measurements had been clean readings of a flaw. 2 decades of photographs, thousands of plates, a discovery that had made the front pages, all of it resolved into the behavior of glass and metal being serviced over the years. The star was real. The gravity was real. The world was not. What remained was a ghost, a planet that existed only in the plates. So the companion that made headlines in the 1960s, the one that put Barnard's star in textbooks and classrooms, was never there at all. Peter van de Kamp had tracked a wobble across photographic plates for decades, and he'd read a giant planet into that motion, something around 1.6 times the mass of Jupiter. The measurement felt solid. It was built on years of patient work at the Sproul Observatory. But the wobble followed the telescope, not the star. Each time the lens got cleaned or adjusted, the star's apparent position shifted in the data. The planet's orbit lined up perfectly with the maintenance schedule, which is exactly the kind of coincidence that should never happen in nature. When other observatories pointed their instruments at the same star, they found nothing. No wobble, no companion, just a quiet red dwarf drifting through the dark. The signal had lived entirely inside one machine's small imperfections. For the man who claimed it, the fallout was permanent. Van de Kamp never accepted the verdict. He'd spent nearly 40 years measuring this star, more than most astronomers spend on any single object, and he kept defending the planet into the 1980s, long after the field had moved on. His own colleagues published the papers that dismantled the claim. One of them worked in the same building. He wasn't a fraud, and no one serious accused him of inventing data. He was careful, meticulous, respected. That's what made it worse. The most rigorous habits in the world couldn't save him from an error baked into his equipment, an error he trusted precisely because he trusted his own hands. The discovery that should have crowned his career became the thing attached to his name forever. When people mention Van de Kamp now, the planet comes first, and the correction comes right behind it. This story is still told today, and not because of the planet. It gets repeated in lecture halls as a warning. When you want a result badly enough, you'll find ways to see it, even in the flaws of your own instrument. The data wasn't lying. The astronomer was reading hope into the noise, and hope is a terrible calibration tool. That's the strange part. The lesson from Barnard's star wasn't about the star, it was about us, about how a careful mind builds a beautiful answer out of nothing and defends it to the end. Astronomy learned to distrust the single instrument, the lone dataset, the tidy signal that fits too neatly. And the star itself paid a price for that lesson. It became the object you brought up when you wanted to talk about mistakes, not discoveries. After the collapse, almost no one wanted to go near this star again. Word travels fast in a small field, and astronomy is a small field. Graduate students heard the story before they heard the science. When someone floated a new observing proposal aimed at this star, the room would go quiet, and someone would eventually make the joke everyone was thinking. The problem wasn't that people thought a planet was impossible there. The problem was reputational. Tie your name to that target and win, you were brave. Tie your name to it and lose, and you were the next cautionary tale in a textbook footnote. So the star sat there, closer to us than almost anything else in the sky, 4 times more massive in myth than in fact, and telescopes pointed elsewhere. The safe move was to study something with no history. For decades, it became a name you mentioned carefully, if at all. The 1970s came and went, so did the 80s. Instruments improved, computers got faster, and the old photographic plates that started the trouble were replaced by electronic detectors far steadier than any human hand guiding a camera through a cold night. And yet the claims didn't come. A few careful surveys logged the star's position, noted nothing unusual, and moved on without fanfare. Nobody wanted to be the one shouting about a companion here, because the last person who did lost everything he'd built over a lifetime of patient watching. There's something quietly sad about that. A star sitting 6 light-years away, close enough to feel like a neighbor, and the smartest people alive kept their distance out of caution. It had earned a grim nickname among planet hunters. They started calling it a graveyard, not because planets died there, but because detections did. Every hint that flickered up in the data seemed to dissolve under a second look, and the pattern held so consistently that some began to wonder if the star itself was jinxed. Of course, it wasn't jinxed. It was just faint, low mass, and demanding. A red dwarf that gave up its secrets grudgingly. The methods of the era simply weren't sharp enough to pull a small signal out of all that noise, so failure after failure piled up like headstones. For a while, it looked like the case was permanently closed, filed under lessons learned. Then, a completely new way of finding planets arrived. The old approach had chased a star's tiny wobble across the sky, trying to catch it drifting sideways against the background. That kind of measurement demanded impossible steadiness, and Earth's atmosphere smeared every attempt. So astronomers stopped trying to see the motion and started trying to feel it instead. The new idea flipped the whole problem. A planet doesn't just get tugged by its star, it tugs back, and that pull moves the star in a small circle over months or years. If you could measure how fast the star crept toward you and away from you, you didn't need to see it shift position at all. That speed left a fingerprint in the star's own light, one that no blurry image could hide. It meant the fragile business of measuring angles could finally be set aside. Instead of watching a star move sideways, they would listen to it breathe. Light carries information in its color, and color is really just wavelength. When something that emits light moves toward you, those waves bunch up and shift slightly toward the blue end. When it moves away, they stretch out and slide toward the red. It's the same effect you hear when a siren drops in pitch as it passes. A star being tugged by a planet does exactly this, first leaning toward us, then away, in a slow rhythm. The shifts are almost absurdly small, sometimes changing the star's speed by just a meter or two per second, the pace of a person walking. Spread that motion across the vast light of an entire sun, and you can start to see the challenge. To read it, astronomers split starlight into a spectrum and watch the dark absorption lines within it slide back and forth. Those lines became a kind of speedometer for a star trillions of miles away. But this method was only as good as the machine measuring the light. Early spectrographs could catch big, close planets slamming their stars around at dozens of meters per second. Barnard's star, if it held anything, would whisper far more quietly than that. So the instruments had to get sharper, and they did, generation after generation. Engineers learned to stabilize temperature and pressure so the machine itself wouldn't drift and fake a signal. They pumped starlight through fibers, locked measurements to precise reference lamps, and squeezed the error down from tens of meters per second toward a single meter, then below it. Each gain opened the door to smaller, colder, more distant worlds. By the 2010s, a handful of spectrographs could sense motions slower than a stroll, steady enough to track a star for years without losing the thread. The precision that once seemed like science fiction had quietly become routine. Eventually, teams felt bold enough to aim these tools back at the cursed star. Barnard's star carried a reputation nobody wanted to inherit. Every young astronomer knew the story of the planets that weren't, the confident claims that dissolved under scrutiny. So when new teams pointed their instruments back at it, they moved carefully, almost quietly, half expecting the star to embarrass them too. This time the approach was different. Instead of watching tiny wobbles on a photographic plate, they measured the star's light itself, splitting it into a spectrum and tracking how it shifted night after night. A machine could sense the star drifting toward us or away at speeds of just a meter or two per second, slower than a person walking down a hallway. They gathered observation after observation, resisting the urge to announce anything. The old wounds were still fresh, and one false alarm here could sink a reputation. Then, deep in the data, faint whispers of a pattern began to appear. It wasn't loud, and it wasn't obvious. Buried in years of measurements, the star's velocity seemed to rise and fall on a gentle rhythm, back and forth, as if something unseen were tugging it in a slow circle. The swing was tiny, around a meter per second, right at the edge of what the instruments could even detect. That was exactly the problem. A signal that faint could be a planet, or it could be the star breathing, flaring, spinning its own dark patches across its face. Barnard's star had fooled people before by pretending its own restlessness was a companion. Nobody wanted to make that mistake again. So they held the excitement at arm's length, a pattern that faint needed more than one telescope and more than one season to trust. To be sure, they pooled everything, from many telescopes and many years. What started as a few cautious teams grew into something larger. Observatories across different continents began comparing notes, and instruments in Chile, in Spain, in the high deserts all trained on the same dim red point in the sky. No single dataset could carry the weight of a claim, so they decided to combine them. It meant reconciling measurements taken on different nights with different machines by people who'd never met. Every source had its own quirks, its own noise, its own way of seeing the star slightly wrong. Stripping all that away without erasing the real signal was painstaking work, and one careless correction could invent a planet out of nothing. They cross-checked, recalibrated, and stacked the records year on year, watching to see whether the faint rhythm survived the scrutiny. Slowly, the pile of data deepened. Together, they assembled almost 2 decades of observations. Think about what that pile actually was. Not one telescope, not one night, but instrument after instrument pointed at the same dim red dot, each adding its own thin sliver of measurement. On their own, any single run said almost nothing. Barnard's star barely moves, and the wobble they were hunting for was smaller than the flicker of the star itself. So they stopped treating the observations as separate stories. They lined them up on a shared timeline, corrected for the quirks of every spectrograph, and let the years overlap. Where one dataset had gaps, another filled them. Where one had noise, the sheer weight of the others helped average it away. That's the quiet power of a long archive. A pattern too weak to see in a season can hold steady across a decade, if you're patient enough to stack it. 19 years of light, folded into a single search. 19 years is a strange amount of time to hold on to a question. Students who started on this data finished degrees and moved on. Instruments were built, upgraded, and retired. Through all of it, the same faint star kept showing up on the observing schedule, one careful measurement at a time. And that long baseline matters more than it sounds. A planet leaves its mark as a slow, repeating tug, and the only way to trust a slow signal is to watch it repeat again and again. One cycle could be a fluke. 10 cycles, spread across nearly 2 decades, start to look like something real. So the team wasn't just adding numbers, they were building the longest, steadiest look anyone had ever taken at this particular star, until the record was deep enough that a genuine pattern would have nowhere left to hide. And out of all that noise, a rhythm finally emerged. It showed up as a gentle back and forth in the star's velocity, a slight shift toward us, then away, then back again. Tiny. A few meters per second, roughly walking pace, buried in data that spanned continents and years. But it kept time. The cycle repeated close to every 233 days. Not once, not twice, but over and over across the combined record, steady enough that the odds of pure chance started falling away. Every fresh slice of data the team folded in seemed to fall in step with the same beat. For a moment, it looked like the thing they'd chased for generations, a real, periodic signal sitting right where a planet might. But they'd been burned before, and everyone in the room knew it. In 2018, they went public, but this time they chose their words carefully. The paper landed in the journal Nature in November 2018, backed by 771 individual measurements gathered over 20 years. Guillem Anglada Escudé and his team weren't guessing anymore. The numbers pointed to something orbiting the star, tugging it back and forth in a slow, steady rhythm. The wobble was tiny, a shift of just 1.2 meters per second, about walking speed, but it repeated every 233 days, clean and regular, like clockwork buried in decades of starlight. That kind of pattern doesn't come from noise. So they gave it a name, the way astronomers do when they think they've found a world. They called it Barnard's Star B, and it was not what anyone pictured. For a red dwarf, you'd expect a planet hugging close, roasting in the glow. This one broke the mold. The mass came out to at least 3.2 times that of Earth, a super-Earth, heavier than our world but far smaller than the gas giants people had chased before. It was rocky, most likely, or a mix of rock and ice, dense enough to hold onto itself under its own gravity, and it was the closest single-planet candidate ever found to a solitary star beyond our own Sun, 6 light-years away, right in our cosmic backyard. But its orbit told a stranger story. Instead of circling tight and warm, it kept its distance. It sat far from the star, in the cold, at the edge of a frozen line. That line has a name, the snow line, the boundary where a star's warmth fades enough for water to freeze solid. Barnard's star B orbited right around it, soaking up only about 2% of the light Earth gets from the Sun. The surface temperature? Somewhere near -170 degrees Celsius, cold enough to lock any water into permanent ice. It wasn't a place for oceans or life as we picture it. It was a dim, frozen shape circling a dying ember, lit by a star so faint you couldn't see it without a telescope. A world in the dark, barely warmed at all. The signal was strong, the data was deep, and the temptation to call it settled was real. This time, the scientists refused to celebrate too soon. They'd seen this movie before. Barnard's star had a way of dangling a discovery in front of astronomers, then yanking it back once someone looked harder. So the team held the champagne on ice and started poking holes in their own work. They ran the numbers again, then again, with different assumptions. They asked whether the signal could be an artifact of how they'd cleaned the data, whether some instrument quirk had crept in over years of observations. Every result got a second reviewer, then a third. Nobody wanted their name attached to the next great Barnard star embarrassment. The candidate looked real, the period looked steady, but looking real had fooled smarter people before, and their caution turned out to be justified. When independent groups went back over the measurements, the tidy picture started to blur. Some analyses recovered the signal cleanly. Others found it flickering in and out depending on which nights they included, which is exactly what you don't want from a real planet. A genuine world orbiting a star should tug on it like clockwork, the same wobble on the same schedule, year after year. This signal didn't always keep time. It faded when it should have held steady and turned up strong in stretches where the physics said it should be quiet. The confirmation that was supposed to close the case wouldn't quite lock into place. The more data they folded in, the shakier the certainty became. The old fear crept back into the room. Every astronomer in that field knows the ghost story by heart. For decades, one man's careful measurements had convinced the world that Barnard's star hosted planets, and every one of those planets had evaporated under scrutiny. The name of that mistake still gets whispered as a warning. So when a fresh signal wobbles, when it won't keep a steady rhythm, the first question isn't what planet is this, it's whether there's any planet at all. The team had to seriously consider that they were chasing the same phantom that had burned their predecessors. Because the thing about Barnard's star isn't just that it's close or that it's old, it's that stars are not the quiet, steady lamps they look like from far away. Because a star, it turns out, can fake a planet all on its own. Here's how the trick works. When astronomers hunt for planets around a star like Barnard's, they're not seeing the planet at all. They're watching the star wobble, a tiny back-and-forth tug as an unseen world pulls on it. That wobble shows up in the star's light, shifting its color by a fraction, over and over, in a steady rhythm. The rhythm is the fingerprint. A real planet returns on the same schedule, year after year, patient and precise. So when a signal repeats, you lean toward a planet. But a star's surface is alive, churning and turning, and it can push that same light around all by itself. That means the very signal you trust can be forged by the star you're studying. The motion looks planetary, the timing looks planetary, and nothing is actually orbiting. For a small, restless red dwarf, that problem is especially cruel. Red dwarfs are covered in dark patches called star spots, cooler regions where magnetic fields choke off the heat. As the star spins, those spots rotate into view and then vanish around the far side. Each pass dims and reddens the light on a regular beat, and that beat can masquerade as an orbit. Barnard's star turns roughly once every 140 days, slow and deliberate for a star. Spots that linger through several rotations paint a signal that repeats on a schedule, exactly the kind of clean rhythm a planet would leave behind. Then there are flares, sudden magnetic eruptions that brighten the star and scramble its light in an instant. So the astronomer is left staring at two possibilities that look nearly identical: a cold world pulling on its star, or a blotchy, flaring surface pretending one exists. Telling them apart is painstaking work, which meant the 2018 signal sat under a cloud of doubt. So Barnard's star B never graduated from candidate to confirmed. The detection was careful, the team was cautious, and still the answer wouldn't settle. Every measurement carried a question mark, because no one could fully rule out the star faking its own companion. The signal was faint, buried in years of data, riding at the edge of what the instruments could resolve. And the closer they looked, the more the star's own restlessness muddied the picture. A planet that might be there, a star that might be lying. No clean way to choose between them. You can't confirm a world you can't separate from its own sun's noise. The tools that found the hint simply weren't sharp enough to end the argument. To settle it, astronomers needed a machine sharper than anything before. Think about what that hint actually asked of us. A planet tugging on Barnard's star would shift it back and forth by less than a meter per second. That's slower than a person strolling across a room, measured across almost 6 light-years of empty space. Older instruments could see motions of a few meters per second on a good night. That's enough to spot a heavy planet in a wide orbit. It's nowhere near enough to catch a small world whispering against a noisy red star. So the deadlock wasn't really about Barnard's star at all. It was about hardware. To break the tie, you'd need a spectrograph that could split starlight finer than anyone had managed, then hold that measurement steady for years without drifting. Building something that precise takes a decade and a mountain. That machine was waiting in a desert in Chile. Its name is Espresso, and it was bolted to one of the largest telescope arrays on the planet. When it came online in 2018, it could detect stellar wobbles down to about 10 centimeters per second. That's the pace of a tortoise, read off a star trillions of kilometers away. The trick is stability. Espresso sits in a sealed vault, temperature controlled to 1/1000th of a degree, pressure held nearly constant, vibrations damped away. Starlight travels down fiber optics into that quiet room, so nothing in the outside world can nudge the reading. It can even combine light from 4 separate 8-meter telescopes at once, gathering enough photons to measure a faint red dwarf with real confidence. This was the instrument the Barnard star question had been waiting for, and it lived under some of the darkest skies on Earth. The telescopes sit on Cerro Paranal, a peak in Chile's Atacama Desert, about 2,600 meters up. The Atacama is one of the driest places on the planet. Some weather stations there have gone decades without measurable rain. That dryness is exactly why it's there. Water vapor blurs and absorbs the light astronomers need, so a bone-dry, high-altitude site gives you air that's steady and clear night after night. Hundreds of cloudless nights a year, far from city glow, with the Milky Way hanging overhead like something solid. Under that sky, 4 giant telescopes track the same faint red star for years, feeding their light into the vault below. There, they could measure a star's motion down to a walking pace. Espresso doesn't measure a star's distance or its brightness. It measures how fast the star is drifting toward you or away, by reading the tiny shift in the color of its light. When a planet tugs on its star, the star wobbles, and that wobble shows up as a shift of a few centimeters per second. Think about that number for a second. A person strolling across a room moves faster than the signal this instrument is built to catch. Espresso can pick out a star nudging at 10 centimeters per second, roughly the speed of a tortoise, across a distance of about 6 light-years. To hold that kind of stability, the whole spectrograph sits in a vacuum, temperature-controlled to a fraction of a degree, isolated from every vibration in the mountain. It's arguably the the steadiest ruler humans have ever pointed at the sky. But raw precision was not enough. They still had to strip away the star's own noise. Barnard's star isn't a calm, quiet lamp. Its surface churns. Cooler star spots drift across the face as it rotates. Boiling plasma rises and falls, and every one of those motions shifts the light in exactly the way a planet would. The star, in other words, fakes its own wobble. That fake signal can be bigger than the real one you're hunting for. So the team leaned on the star's rhythm. Spots come and go on the star's rotation cycle, so signals tied to that cycle get flagged as the star talking, not a planet. A true planet keeps a steadier, separate beat. They gathered hundreds of measurements across years, then modeled the noise and subtracted it, watching to see what refused to disappear. If a signal survived all that filtering, it had a real chance of being a world. In 2024, they finally had something solid to say. The results came from more than 150 nights of espresso data, some of it stacked with earlier observations from other instruments. After all the star's noise was peeled back, a signal held firm. A small, regular tug, repeating every 3.115 days. That shorter period means a planet whipping around Barnard's star incredibly close in, far tighter than Mercury hugs the Sun, and the mass they pulled out was tiny, at least 0.3 times the mass of Earth. This wasn't a gas giant. It was a rocky world, one of the lightest ever found by this method. For a star that had burned scientists twice before, this was a careful, hard-won detection, built on the steadiest instrument they had. The planets were real, but not the ones anyone had announced before. Espresso's data confirmed 4 signals. Not the super-Earth announced in 2018, not the frozen planet that had made headlines. These were different objects, quieter in the data, harder to pull from the noise. The team cross-checked against stellar activity cycles, rotational periods, magnetic field models. They tested every combination of noise sources. The 4 signatures held. They weren't artifacts of star spots drifting across the surface or flares kicking the spectrum around. Each planet tugged Barnard's star with a velocity shift measured in centimeters per second. The lightest pulled at 40 centimeters per second, barely faster than a crawling infant. To detect that against a star's own convective churning required 5 years of near-nightly observations and sub-meter per second stability from the instrument. There were several of them, and they were tiny. The innermost planet, Barnard B, clocked in at 0.4 Earth masses. That's lighter than Mars, heavier than Mercury. The next 3 ranged between 0.6 and 1.1 Earth masses, all sub-Earth or near twins. Together they formed a compact system pressed against the star. Barnard B sat at 0.02 astronomical units, the outermost at 0.13 AU. For scale, Mercury orbits our Sun at 0.39 AU. These 4 worlds fit inside a sphere smaller than Mercury's track around the Sun. Red dwarfs burn cooler and dimmer than G-type stars, so their habitable zones hug closer in. But this was tighter than that. The planets occupied the inner precinct where radiation and tidal forces compete, where atmospheres thin and surfaces bake or strip away. They orbit so close that a year lasts only days. Barnard B completes 1 orbit every 3.15 Earth days. The second planet takes 4.12 days, the third 6.74, the fourth just over 10. At those distances, the star's gravity locks rotation to orbit, one face forever turned toward the red glare, the other frozen in permanent night. Surface temperatures depend on atmosphere, but without thick insulation, the day side likely bakes above 200 degrees Celsius. The night side drops below the freeze point of CO2. Between them, a narrow ring where heat redistributes, if winds can carry it fast enough. Barnard's star is old and magnetically active. Flares erupt irregularly, showering the inner system with X-rays and charged particles. At 0.02 AU, Barnard B receives 9 times the irradiation Earth gets from the Sun. The outermost planet still receives 2.5 times. None sit in the conservative habitable zone, and all endure stellar weather strong enough to strip unshielded atmospheres over geologic time. And the cold, frozen world from 2018 was nowhere among them. Think back to 2018 and that first tentative signal. It pointed to a single super-Earth, roughly 3 times our planet's mass, orbiting far enough out that its surface would sit near -170 degrees Celsius. A frozen world, locked in permanent twilight. For 6 years, that candidate was the face of Barnard's star. The new data left no room for it. The precise radial velocity measurements found no periodic wobble at that distance, no mass hiding in the cold. The planet that launched 100 headlines simply wasn't there. What earlier instruments read as a world was noise, stellar activity dressed up as gravity. So the frozen super-Earth quietly dissolved, not disproven in a dramatic moment, just absent when better eyes finally looked. Once again, the map of this system had to be redrawn from scratch. In its place stood something stranger and smaller. 4 confirmed planets, each between 0.2 and 0.34 times Earth's mass, orbiting in tight, fast loops. The innermost completes a full year in about 3.15 days. The outermost finishes in under 7. All 4 huddle closer to Barnard's star than Mercury sits to our Sun. Their orbits would fit comfortably inside the space between us and our own star, with room to spare. This isn't a scaled-down copy of the solar system. It's a compact, crowded family of worlds packed into a sliver of space. The system that had been imagined as one lonely ice ball was now a busy inner court of rocky bodies. Every assumption from 2018 was gone, rewritten line by line. But confirming the planets only sharpened a harder question. Knowing where these worlds are tells you almost nothing about what they're like. Mass and orbit are just numbers on a page. Whether any of these planets holds an atmosphere, whether liquid water could ever pool on a surface, whether the chemistry of life could take hold, all of that stayed blank. And the odds looked hard from the start. These 4 worlds orbit so close that their daytime surfaces likely bake past 100 degrees Celsius. The radiation pouring off the star hits them relentlessly, year after year, with nothing yet known to shield them. So the discovery answered one question and opened a deeper one. Finding rock is easy compared to finding refuge. The real puzzle wasn't whether planets existed here, but whether any of them could ever be more than scorched stone. And red dwarfs carry a reputation their gentle glow hides. A red dwarf like Barnard's star burns cool and dim, giving off a fraction of the light our sun pours out. To stay warm, a planet has to huddle in close, orbiting in days instead of years. And that closeness comes with a price no amount of distance from us can soften. These stars are stingy with warmth, but generous with something else. A tight orbit means bathing in radiation, sitting inside a magnetic field that never quite settles down. Over billions of years, that steady bombardment can strip an atmosphere clean, peeling away the very blanket a world would need to hold on to heat and water. So the calm you'd imagine from a faint red glow is a trick of scale. What looks gentle from light years away is anything but up close. These small stars are famous for lashing out with sudden violence. There's a second problem baked into that closeness. When a planet orbits this near, the star's gravity grabs hold and slows its spin until the rotation matches the orbit. The world stops turning against its sun. Astronomers call it tidal locking, and it means one hemisphere faces the star forever, while the other stares out into permanent night. There's no sunrise, no sunset, no day rolling into evening, just a fixed point of red light nailed to one side of the sky and total darkness on the other. Picture standing on that boundary line, the Terminator, where blistering day meets endless dark. The temperature difference across a single world could be staggering, driving winds and forces we barely understand. One side scorched, one side frozen, and that was the gentlest problem. So the question splits scientists down the middle. Some argue a thick enough atmosphere could carry heat from the day side to the night side, smoothing out those extremes and leaving a habitable strip somewhere between fire and ice. Others counter that the flares and radiation would tear that atmosphere apart long before anything could take hold. Both sides have models, and both models are convincing on paper. The trouble is that a model is only as good as the world it's tested against, and no one had ever measured the air on a planet like this. Everything hinged on a single unknown, whether an atmosphere was there at all. You can't argue your way to that answer. You have to go look, and looking meant catching the faint warmth of a small rocky world drowned in the glare of its star. Settling that argument would take an instrument that could read heat itself. So they built the machine for exactly this problem. The James Webb Space Telescope launched on Christmas Day 2021, folded up like origami inside a rocket, then unfurled a golden mirror 6.5 meters across 1,000,000 miles from Earth. It's the largest telescope humans have ever flown, and it was made to see the things that hide from ordinary starlight. For years it had been staring at the early universe, at galaxies born just after the Big Bang, but a telescope that can catch light from 13 billion years ago can also turn its attention much closer to home. And Barnard's star, sitting just 6 light-years out, had unfinished business. So the astronomers pointed it at our neighbor and waited. Whatever warmth those rocky worlds carried, if any, Webb was built to feel it. Webb sees in infrared, in the wavelengths where secrets hide. Here's why that matters. Your eyes read visible light, the stuff the sun pours out, and the stuff a bright star drowns everything in. But heat radiates in infrared, longer wavelengths your eyes will never register, and that's exactly where a small warm planet gives itself away. Webb's detectors are chilled to around 40 Kelvin, roughly -233 degrees Celsius, so the telescope's own warmth doesn't blind them. That cold lets it pick up faint thermal glows and, more than that, split incoming light into a spectrum. Slice light finely enough, and you can read the chemical signatures of an atmosphere, water, carbon dioxide, methane, each leaving its own fingerprint. No instrument before it could do this for worlds so small and so close to their star. It was a new kind of sight aimed at an old, stubborn question. For the first time, that gaze locked onto our fast-moving neighbor. The target list was specific. 4 rocky planets, none larger than about a third of Earth's mass, whipping around Barnard's star in orbits measured in days, not years. The innermost circles its sun in a little over 2 Earth days, close enough that the whole system fits well inside the orbit of Mercury. Webb had to isolate the faint infrared trace of those tiny worlds from the overwhelming light of the red dwarf right beside them. It's like trying to hear a whisper standing next to a jet engine. The margins were brutal, and a single misread could send the whole conclusion the wrong way. So the observation was planned down to the minute, the pointing locked, the detectors ready. It was hunting for the faint thermal fingerprints of worlds and atmospheres. Every object with a temperature glows in infrared, and that glow is a fingerprint. Webb wasn't looking for a pretty picture. It was reading heat, the faint warmth radiating off anything orbiting a star just 6 light-years away. If a planet held an atmosphere, the gases in it would absorb specific slices of that light, carving dark notches into the spectrum. That's what the team was hunting: carbon dioxide, water vapor, methane. Each one leaves a signature at a known wavelength. Find the notch, and you've found the gas. Miss it, and you've learned something too. The plan was to separate the planet's feeble thermal signal from the overwhelming blaze of the star itself, a contrast problem measured in parts per million. Get the subtraction wrong by a hair, and a real atmosphere vanishes into the noise, or worse, noise pretends to be an atmosphere. So they weren't just collecting light. They were collecting the raw material for a verdict on whether these worlds could hold anything at all. The observation window opened, and the data began to flow. The campaign ran in carefully timed blocks. the telescope holding its aim on a target barely more than a dim red ember from here. Webb sits about 1.5 million kilometers from Earth, parked at the second Lagrange point, shielded from the sun by a barrier the size of a tennis court. That cold, dark stability is the whole point. Its instruments run near 40 Kelvin, so their own heat doesn't drown out the faint signals they're built to catch. For hours, the detectors stared, gathering photons one by one, stacking exposure on exposure to pull signal up out of the dark. Barnard's star is a flare star, restless, prone to sudden brightening, and that made the timing delicate. A burst at the wrong moment could contaminate a reading. So the team watched the light curve as it came, noting every fluctuation, flagging anything that moved when it shouldn't. Nothing was assumed clean. Every second of that window was accounted for. Then the spectra arrived, and the analysis began. The raw data traveled 1.5 million kilometers back to Earth, funneled through the deep space network, then routed to the science team as files that meant nothing yet. This wasn't a finished spectrum. It was detector counts, columns of numbers riddled with cosmic ray hits, thermal drift, and the fingerprints of the instrument itself. Before anyone could ask what the star was telling them, they had to strip out everything that wasn't the star. Bad pixels flagged, cosmic ray strikes removed, the background subtracted, the wavelengths calibrated against known references. Only then does raw signal become something you can read. And with margins this thin, a single overlooked artifact could masquerade as a discovery or bury a real one. So nobody trusted the first pass. Every line of that light had to be checked, twice over. So they slowed everything down. The raw spectra came in as a jagged mess of counts, and the first job was calibration, stripping out the fingerprints of the telescope itself. Detector noise, thermal drift, the faint glow of the instrument's own optics. All of it had to be modeled and subtracted before a single real feature could be trusted. Then came the cross-checks. Each exposure was compared against the others, frame by frame, so no stray cosmic ray hit or hot pixel could sneak through disguised as a chemical line. They ran the pipeline, then ran it again with different settings to see if the shape held. Anything that shifted got flagged. And through all of it, they said nothing. No preprint, no email chain, no quiet word to a colleague down the hall. The result stayed locked inside a handful of machines while the team tore at their own work, trying to break it before anyone else could. And buried in the light was something that stopped them cold. It sat in a narrow band of the infrared, a feature that had no business being there. Not a smooth dip, not the gentle absorption you'd expect from a quiet atmosphere or bare rock. It was sharper than that, and it didn't match the templates they'd loaded in expecting a dead, sun-baked world. Their first instinct was to distrust it. They pulled the raw frames back up, isolated that slice of wavelength, and stacked the exposures to see if the shape survived the averaging. It did. The signal was faint, but it stayed put, sitting exactly where it had appeared the first time. That's when the mood in the room changed. A feature that repeats isn't noise, and a feature that repeats where nothing should be is a problem you can't file away. They kept the numbers to themselves a while longer because they knew what a claim like this would cost if it were wrong. Which brings us back to the silent room where this story began. Picture it again, but now you know what they were looking at. The screens up front, the plotted spectrum glowing against a dark background, and a small group of people who had checked this thing more times than they could count. Nobody was talking. Everyone was staring at the same stretch of the curve. This was the moment the cold open dropped you into, before you had any of the context. The years of watching Barnard's star, the argument over whether its planets could hold on to anything like an atmosphere, the careful stripping of every instrument artifact. All of it funneled down to this one plot on this one screen. And the feature that had refused to disappear was right there in front of them, plotted in full. The reading was not a smooth curve, it was a spike. Picture the shape of it. Across most of the wavelength band, the light held steady, the slow, patient glow you'd expect from a red dwarf that's been burning for billions of years. Then, At one point, it jumped. A sharp climb where nothing should have moved. The brightness didn't drift up and settle. It shot past the baseline and came back down, a narrow tower standing over a flat plane of data. In the infrared, that kind of vertical jump means energy, and a lot of it released fast. That's what made the room go quiet. A steady star doesn't do that. Something had dumped a burst of power into the light Webb caught, and the instrument had recorded every step of it. But a spike on a plot is not proof of anything yet. Their first job was to prove it was not another ghost. So they went backward through the pipeline. Every telescope has quirks, and Webb is no exception. A single overheated pixel, a cosmic ray clipping the detector, a rounding error buried in the calibration files. Any of those can fake a signal that looks real. They pulled the raw frames before any processing touched them. They checked the dark current, the flat fields, the corrections applied for the detector's own temperature. They compared the spike against known artifacts, the fingerprints bad data usually leaves behind. If the feature was a glitch, it should have shifted or vanished when they changed the reduction steps. It didn't. They reran the analysis with different software, different assumptions, different people at the keyboard. Each pass was a chance for the spike to fall apart and admit it was noise. This time, every check came back the same. That word, same, carried weight none of them said out loud. For decades, Barnard's star had been a graveyard for false positives. Peter van der Kamp spent years tracking a wobble he was certain meant planets, and it dissolved the moment someone cleaned his telescope's lens. His signal had been an artifact all along. This was the opposite. The harder they pushed, the more solid the feature became. It didn't retreat under scrutiny, it held, frame after frame, method after method. Webb had seen something, and the data refused to take it back. So they stopped asking whether it was an error, and started asking what it was. The answer was already sitting in the shape of the light, in that vertical wall of energy climbing off the baseline. The spike was the star itself, erupting. What Webb recorded wasn't a slow flicker, it was a sudden release, a burst of energy tearing off the star's surface in a matter of minutes. Barnard's star is a red dwarf, small and dim by our standards, but small doesn't mean quiet. These stars store magnetic tension in twisted field lines, and when those lines snap, the energy comes out all at once. The eruption Webb caught pushed the star's brightness up sharply in the ultraviolet and X-ray range, the parts of the spectrum that do real damage. For a red dwarf this old, that kind of output is startling. It's the sort of event that lasts only moments in the data, yet carries a punch far above what the steady starlight ever suggested. And that's the part that changes the story. This isn't a background hum. It's a violent, repeating outburst from a star that sits just a few light-years from us. And that eruption bathed its close-in planets in something lethal. To understand why that matters, look at where the radiation goes. A flare doesn't just brighten the sky for whatever orbits nearby. It floods those worlds with ultraviolet and X-ray photons energetic enough to break molecules apart. Water vapor, methane, the building blocks an atmosphere depends on, all of it gets ripped into pieces at the chemical level. Then comes the stripping. High-energy radiation heats the top of a planet's atmosphere until gas molecules move fast enough to escape into space. Over enough flares, over enough time, the air simply bleeds away. The surface below loses its shield against the next round, and the next. Life, at least the kind we know, needs a stable buffer between it and its star. Repeated sterilizing bursts don't allow that buffer to hold. The chemistry never gets the quiet stretch it needs to build anything lasting. Any atmosphere clinging to those planets would struggle to survive it. Now factor in distance. The planets circling Barnard's star hug it tightly, orbiting in a matter of days rather than months. They have to, because the star is faint, so the only warm zone sits close in. That closeness is exactly the problem. The nearer a world orbits, the harder every flare hits it. A planet like Earth has help. We sit behind a global magnetic field that deflects charged particles. and we're a comfortable 93 million miles from a stable star. These worlds have neither luxury. A weak or absent magnetic field means the radiation reaches the surface with almost nothing in the way. And the flares don't come once. They return, again and again, across the star's long life, each one chipping away at whatever protection might have formed. There's no recovery window, no shelter to retreat to, which points to a bleak picture of what these worlds really are. So picture the worlds we've actually confirmed circling Barnard's star, at least 4 small planets, each less than a third of Earth's mass, hugging their star in orbits that take just a few days to complete. They sit so close that any one of them catches the full force of every flare, over and over, with nowhere to hide. These aren't the temperate, blue marble worlds you'd hope to find around the nearest single star to our Sun. They're baked, blasted rock, their surfaces likely stripped of any atmosphere long ago. Whatever water might have started there would have been boiled off and scattered into space. It's a quiet kind of loss, 4 worlds that were always going to come up empty, sterilized before anything could ever take hold. And when scientists sat with that result, one detail cut deeper than the rest. The cruelest part was the age of the star doing this. Barnard's star isn't young. Estimates put it somewhere between 7 and 10 billion years old, older than our Sun, older than Earth, possibly older than most of the stars you can see on a clear night. That's nearly the full stretch of time our galaxy has existed. This little red ember has been burning since the Milky Way was still assembling itself, watching generation after generation of stars ignite and die while it just kept glowing, slow and steady and impossibly patient. 10 billion years is enough time to settle down, to spend your fury and drift into a long, quiet old age. That's what the textbooks would predict for a star this ancient. An ancient star should be calm, and this one is anything but. Red dwarfs are supposed to mellow as they age. They spin slower over billions of years, their magnetic fields weaken, and the violent flaring of their youth is meant to fade into a gentle hum. By 10 billion years, Barnard's star should be a burned-down candle. Instead, the instruments caught it mid-tantrum, throwing out flares like a star a fraction of its age. Something is still winding this thing up, keeping its magnetic engine tight and loaded after all this time, and nobody expected to find that kind of energy in a star this far past its prime. That's the part that sits wrong. Not just a hostile star, but one that has stayed hostile for longer than the Earth has existed, and shows no sign of stopping. And this restless, hostile star is not staying at a safe distance. Every star in the sky is moving, drifting through the galaxy on its own path, but most of that motion happens so far away it barely registers over a human lifetime. Barnard's star is different. It carries the largest proper motion of any star we've ever measured, sliding across our sky fast enough that astronomers have tracked its position shifting for over a century. And it isn't just moving across our line of sight, it's coming toward us. The whole system, the star and its scorched little worlds, is falling through space in the Sun's general direction, closing the gap year after year after year. Right now it sits second from us, close, but not the closest. That won't stay true. The distance is shrinking, and it will keep shrinking long after everyone alive today is gone. In the far future, it will become our closest stellar neighbor of all. The calendar for that is longer than any story humans have ever told. In roughly 11,000 years from now, Barnard's star reaches its nearest point to the Sun, its closest approach in the whole span of its orbit through this part of the galaxy. At that moment, it will have crept into about 3.75 light-years from us, closer than Proxima Centauri, closer than anything else in the neighborhood. For a while, this restless red dwarf will be the nearest sun to our own, hanging in the dark just beyond our doorstep. So picture it, a star we've watched erupt, a star that has sterilized its own planets for billions of years, quietly closing the distance until it holds the title of our closest neighbor. That sounds like a threat, and the reality is stranger than that. Here's what 3.75 light-years actually means. That's still more than 35 trillion kilometers of empty space. Even at its closest, Barnard's star stays impossibly far, far too distant to touch our planets, our orbit, or the Sun itself. Its flares, however violent, fade to nothing across that gulf. So the approach changes the map, not the danger. It rearranges which lights are nearest in our sky, shuffles the local order of stars, and gives future skywatchers a new closest companion. Nothing about it puts Earth at risk. The gravity is negligible, the radiation is negligible, the whole encounter is a slow, gentle pass in the dark. Which makes the reaction to all this harder to explain. If the motion is harmless and the distance is safe, then the unease scientists felt looking at this data has to be coming from somewhere else entirely. Because what actually rattled scientists was not the star hitting us. It was what the star had been doing the whole time, quietly, while everyone filed it under harmless. For decades, Barnard's star was the textbook example of a calm, elderly red dwarf, the boring old neighbor you never worried about. Webb looked closer and found something that had been erupting the entire time we were calling it steady. A star we treated as gentle turned out to be capable of violence that would scrub a planet's surface bare. That alone would be unsettling, but the part that landed hardest was the category it belongs to. Red dwarfs like this one aren't rare. They are the most common kind of star in the galaxy, roughly 3 out of every 4 stars burning right now. So the thing we misjudged in our own backyard isn't an exception, it's the default setting for most of the universe. That single realization pulled the whole century of this story together. Think about what Webb actually stitched together here. An age of nearly 10 billion years, more than twice the Sun's, a star that should have long since gone quiet. A path through space so fast it crosses a full moon's width of sky every 180 years, the quickest proper motion we've ever clocked. And then the flares, sudden and brutal, from an object old enough that nobody expected it to have any fire left. Each of those facts had been sitting in the record separately, treated as its own curiosity. Age in one paper, motion in another, activity in a third. Put them side by side, and they stop being 3 oddities and become one coherent portrait of a star that is old, fast, and still dangerous all at once. That combination is exactly what the earliest observers were staring at without the tools to read it. And it finally explained that first silent reading. Go back to where this started. A single, quiet line on a screen, a signal in the dark that made a room full of experts go still. For a while, nobody could say what it meant, only that it didn't fit the calm star they thought they were pointing at. That reading was the flare. It was the ancient, hostile pulse of a star we'd written off as safe, caught by an instrument finally sensitive enough to see it for what it was. The thing that unsettled scientists wasn't a mystery signal at all. It was proof that our picture of the closest single star to the Sun had been wrong for 100 years. The loop that opened with that silent reading closes right here, on the light itself. Getting here meant admitting how long we had been wrong. Think about what that century actually cost. Astronomers pointed their best instruments at Barnard's star for decades, and again they saw things that weren't there. Peter van der Kamp spent 30 years convinced he'd found planets wobbling that star, publishing the claim, defending it, staking a reputation on it. The wobble turned out to be his telescope, not the sky. Tiny shifts from lens adjustments at Swarthmore's observatory masqueraded as worlds. A careful, brilliant man chased a ghost for most of his working life and never let it go. That's the quiet tragedy under all of this. This one faint red dot, only 6 light-years away, kept fooling the people who studied it hardest. In the end, the so-called curse was finally broken. It took a completely different kind of measurement to do it. Instead of watching for a star to sway on a photographic plate, modern teams measured the light itself, tracking shifts of barely a meter per second in how the star moves toward and away from us. That's the pace of a slow walk, read across 6 light-years of empty space. Where Van der Kamp's era saw phantoms, this generation finally pulled real signals out of the noise, confirmed them, and ruled the false ones out. The failures weren't wasted. They mapped every wrong turn so this attempt could avoid them. Every rejected wobble, every corrected instrument, every disappointment fed into a method precise enough to succeed. For the first time, we can describe this system as it actually is. So here's what's really out there. A red dwarf about 16% the Sun's mass, ancient beyond easy comprehension, still snapping with flares that would scour anything close, and orbiting it, 4 confirmed planets, a world so tight against that star it races around in a matter of days. These aren't gentle sunlit places, they're seared, radiation-battered rocks locked in blistering close orbits, circling a star that has been burning for longer than the Sun has existed and will keep burning for trillions of years more. That's the honest portrait. No phantoms, no wishful worlds, just a small, violent star and its scorched companions, finally seen clearly. And that view is a warning about far more than one star. Here's what makes Barnard's star matter beyond its own scorched planets. It isn't a freak, a one-off oddity spinning alone in the dark. It's a textbook example of a red dwarf, the runt class of stars that burn cool, burn slow, and burn for a very long time. What Webb saw here, it could see almost anywhere it pointed. The flares, the tight cramped orbits, the radiation baths that strip a planet's air, none of that is unique. Look at one red dwarf and you're glimpsing the behavior of billions more just like it. So this single star, 6 light-years away, becomes a kind of stand-in for a whole population. When you understand how Barnard's star treats the worlds around it, you've learned something about the fate of countless worlds you'll never name. And that scale is easy to underestimate, because these small, angry stars are the most common kind in the galaxy. Count the stars in the Milky Way, and something surprising jumps out. Sun-like stars, the yellow, steady ones we tend to picture, make up only around 7% of the total. Red dwarfs, the small dim ones like Barnard's star, account for roughly 70 to 75%. 3 out of every 4 stars in the galaxy are these cool little furnaces. Our Sun isn't the standard model, it's the exception. If you picked a random star out of the hundreds of billions overhead, the odds say you'd land on a red dwarf, not a twin of our own. So the galaxy isn't mostly bright and warm and generous, it's mostly dim, cramped, and prone to violent tempers. And when the most common star turns out to be the harshest kind, that reframes one of the biggest questions we ask about the universe. That question is simple: is anyone else out there? For decades, the math felt hopeful. Billions of stars, billions of planets. Surely life had room to appear somewhere. But if most of those stars are red dwarfs, the hopeful math starts to buckle. Think about what a planet has to survive to sit in a red dwarf's habitable zone. It has to orbit close enough to feel every flare, every burst of radiation that can peel an atmosphere away over time. It likely gets locked with one face in permanent daylight and the other in endless freezing night. The gentle, stable conditions life seems to need are exactly what these stars refuse to give. So the most abundant real estate in the galaxy may also be the most hostile. The cosmos could be crowded with worlds and still be nearly empty of life, not because planets are rare, but because the wrong kind of star is everywhere. It is a sobering answer, and worth sitting with. Think about what that really costs us. For decades, red dwarfs looked like the galaxy's great hope, small stars that burn for trillions of years, giving life all the time it could ever need. Patience was supposed to be their gift. And then you look closer, and the patience turns out to be a slow furnace. Those same stars spend their youth throwing flares that strip atmospheres bare, and by the time they calm down, the damage is already done. The clock that seemed generous was running against life the whole time. Barnard's star sits 6 light-years away, close enough to feel like a neighbor, and it carries that same quiet verdict. Not a villain, not a threat, just a fact that reshapes the odds for billions of worlds we'll never visit. It's easy to want a louder ending than this, stripped of drama, what Webb confirmed still stands on its own. So set the story aside and look at the measurements. Webb, working with years of radial velocity data, helped pin down at least one small planet circling Barnard's star, a world only a fraction of Earth's mass, whipping around its star in a matter of days. It orbits far too close for liquid water, baked by a red sun that fills its sky. The telescope's instruments can read starlight finely enough to catch the faint tug of worlds lighter than our own, and to study the environment those worlds are born into. That's the real leap. We went from arguing whether planets were there to describing what they're made of and what they endure. A star that fooled astronomers for half a century finally gave up honest numbers. No phantom gas giant, no habitable oasis, just a small, scorched world and a star that will outlast almost everything. The question now is what all of this means for you. Because Barnard's star isn't some distant abstraction, it's one of the closest stars to our Sun, part of the handful of neighbors that will drift past us over the coming millennia. When we map its planets and its flares, we're really sketching the character of the space right outside our door. And what that map shows is a kind of loneliness we didn't fully expect. The nearest stars are mostly these small red furnaces, common and cold-hearted toward life. The warm, steady stars like ours turn out to be the rarer neighbors, scattered thinly through a crowd of red dwarfs. That makes our own quiet, stable sun feel less like a default and more like a piece of luck we've been standing on without noticing. Understanding Barnard's star is really a way of understanding the room we live in. It starts with what this says about our own corner of space. Think about how close Barnard's star actually is. Just 6 light-years out, it's the nearest single star to the Sun, and only the Alpha Centauri system sits nearer. Yet for the better part of a century, we couldn't say for certain whether anything orbited it. We were guessing about our own front porch. That gap between nearness and knowledge is humbling. Van de Kamp stared at this star for 40 years and still got the answer wrong. The light reaching his telescope had left Barnard's star only 6 years earlier, practically the present tense in cosmic terms, and even that wasn't enough to see clearly. It took instruments that could measure a stellar wobble of barely a meter per second to finally read what was there. A rocky world, about 30% the mass of Earth, whipping around every 3.15 days. We share a neighborhood we're only now learning to map, and the search for answers is only accelerating. Barnard's star isn't finished with us. The radial velocity teams that found that little planet in 2024 are still watching, tightening their numbers, testing whether one or more faint companions hide in the noise. Every month of data sharpens the picture a bit more. And it's not alone under the microscope. Red dwarfs make up roughly 3/4 of the stars in our galaxy, so instruments like ESPRESSO and the coming generation of extremely large telescopes are turning toward hundreds of them. Each one is a chance to catch a small world in a tight, fast orbit. The techniques that finally cracked Barnard's star are now standard practice, pointed at neighbor after neighbor. Every faint, cool star on that target list is a place where the same story could play out again. Every one of them carries the memory of a ghost planet. Which brings us back to Peter van de Kamp. He wasn't careless. He was meticulous, devoted, and completely convinced by data that turned out to be an artifact of his own telescope's tweaks and cleanings. For decades, textbooks carried his phantom worlds as fact. When other astronomers failed to reproduce his wobble in the 1970s, the claim quietly collapsed. He defended it to the end of his life, believing in planets that were never there. It's a hard thing to sit with, a career's centerpiece dissolving into an equipment glitch. But that failure became a lesson every exoplanet hunter now carries. Check your instrument before you trust your signal. Demand that someone else can see what you see. His mistake, oddly, is one of science's quiet triumphs. Look at the whole arc, and something clicks into place. Peter van de Kamp watched Barnard's star for decades and reported planets that weren't there. Then other astronomers pointed their own telescopes, ran their own numbers, and the phantom worlds dissolved. That wasn't a failure of science. That was science doing exactly what it's built to do. Every claim about this star got tested again, with better tools, by people who owed Van de Kamp nothing. The 1970s brought sharper measurements. The 2010s brought precision radial velocity. Webb brought the deepest infrared look yet. Each generation checked the last one's work instead of taking it on faith. That's the quiet machinery underneath all of it. Not one brilliant person being right forever, but many careful people refusing to stop asking. The claims that survived earned it. The claims that didn't fell away. The real strength was never certainty. It was doubt. Doubt gets a bad reputation. We treat it like weakness, like the thing that stops us from committing to an answer. But in this story, doubt is the hero. It's what made astronomers re-examine a beloved result from a respected man and say, gently, we think this is wrong. Humility is what let them measure Barnard's star for 100 years without ever declaring the case closed. Every generation assumed it might be missing something. That assumption is exactly why they kept looking, kept refining, kept catching the errors the last round left behind. The planets that turned out to be real, the small ones Webb and its partners confirmed, only stand because everything false was stripped away first. Being willing to be wrong is what made the truth possible, and through it all, the star simply kept moving. Because that's the one thing that never changed. While humans argued over phantom Jupiters and refined their instruments and rewrote the textbooks, Barnard's star kept sliding across the sky. It moves faster against the background than any other star we know, about 10.3 arcseconds a year. That's what caught E. Barnard's eye back in 1916. Not brightness, not color, just relentless motion. In a human lifetime, it shifts a distance on the sky roughly equal to the width of the full moon. Every measurement in this whole saga was really just us trying to keep up with something that won't sit still. And it isn't only crossing our view, it's coming closer, drifting through space on a path that brings it nearer to the sun than it is right now. It is heading for its closest pass long after we are gone. That closest pass sits about 11,000 years in the future. Put that number against a human lifetime and it stops feeling like a date and starts feeling like a distance. 11,000 years ago, the last ice age was still loosening its grip, and no one had yet planted a field or written a word. Barnard's star will keep sliding along its path the entire time, shaving off a fraction of light years, closing the gap between it and the sun with the patience only gravity has. It won't hurry for us. It won't wait for us either. It simply moves, the way it has for billions of years already. When it finally reaches that nearest point, the sky above Earth will have quietly rearranged itself, and this red dwarf will glow a little brighter in whatever eyes are watching. By then, no one who worked on this story will remain to see it. That's the strange gift of studying a star like this. You spend a career, maybe a whole field spends decades, chasing a signal that resolves over spans no person will ever witness end to end. The flare Webb caught lasted minutes. The journey it belongs to runs for millions of years. Every astronomer who measured Barnard's motion, every failed planet claim, every fresh instrument pointed its way, all of it is a brief flicker inside a story that started long before us and keeps going long after. We get to hold one small piece of it for one small window and then hand it forward. There's something quietly humbling in that, knowing the work outlives the workers and the star outlives the work. We are a short chapter reading a very long book, so it is worth remembering how we got here. It began with a fast-moving speck that Edward Barnard clocked in 1916, a dim red dwarf racing across the sky quicker than any star we knew. For decades it teased us with planets that never held up, worlds announced with confidence and then quietly erased when better data arrived. Then sharper tools narrowed the search, trimming what could be hiding there down to small, close-in worlds and confirming a rocky companion tucked against the star. Webb added the final piece, watching that faint sun flare and measuring what that violence would do to anything orbiting near it. A century of patience, correction, and better questions all pointed at one of our nearest stellar neighbors. We started with a moving dot and ended with a portrait, sharp enough to say what kind of place this really is, which leaves one last thing to say. So what did Webb actually find when it stared at Barnard's star? Not a monster, not a warning, just a small, cool red dwarf, 6 light-years away, doing what red dwarfs do, flaring and churning and throwing radiation across the little worlds that circle it too close for comfort. The word rattled wasn't an exaggeration. It was about surprise, the kind scientists feel when a star they thought they understood turns out to be busier and harsher than the textbooks let on. Every flare rewrote a paragraph. Every measurement narrowed the odds. What lingers isn't dread, it's the quiet realization that even our closest neighbors keep secrets, and that it took a century of watching one faint point of light to pull a few of them loose. And where things stand now is simple enough to state plainly. No sirens, no countdown. Barnard's star doesn't know we're looking, and it wouldn't change course if it did. It just keeps moving, the way it has for billions of years, indifferent to the telescopes trained on it. We gave it names and numbers and a place in our catalogues. We tracked its wobble, mapped its planets, and measured the tempers of its flares. And in return, it gave us a cleaner picture of what a small red star and its cramped little worlds are truly like. That's the whole arc. A moving dot, 100 years of careful eyes, and finally, a face to put to the name. Nothing more dramatic than that, and nothing less remarkable. This is where the story rests today. Here's the plain version. Barnard's star has at least one confirmed planet, a world roughly a third of Earth's mass, orbiting in just over 3 days, far too hot to hold life. Its flares are real and measured, sterilizing any surface that sits that close. And the star itself is still racing toward us at about 200. In roughly 11,000 years, it'll make its closest pass, sliding just under 4 light-years away, the nearest it'll ever come. Then it keeps going, the way it always has. No collision, no threat, just a slow drift across a sky most of us will never see change. Go back to Peter van der Kamp's plates for a second, because the scale of it is easy to miss. He measured star positions down to fractions of a micron on glass, tracking shifts smaller than the width of a human hair held at arm's length. To claim a planet, he was reading a wobble of about 0.02 arcseconds, roughly the angle a coin makes from 60 miles away. That's what makes the failure so quietly brutal. The signal he saw was never in the sky. When his own colleagues plotted the timing of the apparent wobble, the kinks lined up with 1949 and 1957, the exact years the Sproul telescope's lens was pulled and reseated for maintenance. Change the glass, change the geometry, and every star on the plate drifts by the same tiny amount. Barnard's star wasn't dancing to a hidden Jupiter, it was standing still while the instrument moved underneath it. So the field pivoted to a completely different question. Instead of watching a star slide sideways across decades, astronomers started listening to its color. When a star is tugged toward us, its light bunches bluer. When it's pulled away, it stretches redder. That's the Doppler method, and it doesn't care how the telescope was bolted together. The catch is how small the tug is. Barnard B pulls its star at well under a meter per second, slower than a casual walk. Detecting that means splitting starlight into thousands of narrow lines and measuring how they shimmy, night after night, for years. That's where espresso comes in, the spectrograph feeding Chile's very large telescope. It sits in a vacuum-sealed, temperature-locked room, isolated so tightly that a single degree of drift would swamp the planet's whisper. The light travels through fiber optics before it's ever measured, so the telescope can shake without corrupting the reading. And here's the part that would have comforted van der Kamp. To pull Barnard B out of the noise, the team had to model the star itself, its rotation, its spots, its slow magnetic breathing. A red dwarf's surface churns, and each dark blotch fakes a Doppler wobble as the star spins. Separating a real planet from a star spot is the whole game now. When the 2024 data settled, the picture was 4 small worlds, not one frozen giant. The confirmed planet, Barnard B, comes in around a third of Earth's mass and whips around the star in just over 3 days. At that distance, it bakes at surface temperatures far too high for liquid water, closer to an oven than a habitable shore. Now sit with what kind of star it's orbiting. Barnard's star is an M dwarf, only about 16% of the Sun's mass and a fraction of its width, barely larger across than Jupiter. It burns so cool and slow that it'll keep shining for 1 trillion years, long after the Sun has swelled, died, and gone dark. That patience is the trap, because a planet warm enough for liquid water has to huddle in tight, sometimes 10 or 20 times closer than Earth sits from the Sun. Get that close to any star and the tides lock you, so one face stares at the fire forever, while the other freezes in permanent night. For a while, the debate was polite. Maybe winds redistribute the heat. Maybe a thick atmosphere smears warmth around to the dark side. Maybe the Terminator, that ring of endless dawn between scorching and frozen, could hold a thin band of survivable ground. Then Webb turned its infrared eyes on the system, not to see the planet's glow, but to read the star's tantrums directly. Where earlier telescopes measured the star as a steady point, Webb's detectors catch the heat signature of individual outbursts, the moments the surface tears open and dumps radiation outward. Red dwarfs are famous for this. A star like Barnard's can double or triple in brightness in minutes during a flare, spitting out X-rays and ultraviolet that a calm star like the Sun rarely matches. And unlike the Sun, these stars stay violent for billions of years instead of settling down. For a planet parked that close, there's nowhere to hide. The same tight orbit that might keep it warm also drops it straight into the blast zone. Each flare rakes the day side with sterilizing ultraviolet, stripping away atmosphere and cracking apart the molecules life would need to even get started. That's the reading that changed the mood in the room. Barnard's star isn't a gentle old ember cradling a quiet world. It's an ancient, restless furnace, still erupting after billions of years, with its nearest planet locked in the crossfire and no shield to catch the worst of it. And this is the uncomfortable mirror. Roughly 3 out of every 4 stars in the galaxy are red dwarfs just like this one. If the closest single star to the Sun is this hostile up close, then the most common address in the universe may be a rough neighborhood for anything trying to live there. So the fear wasn't a monster in the dark, it was recognition. The star that broke one astronomer's career, then hid its real planets for another 60 years, turned out to be typical, not exotic. The galaxy is full of these small, cold, furious suns. That's Barnard's star as we know it now. Confirmed planets, measured violence, and a steady approach we can predict to the year. If you like following faint dots until they turn into real places, subscribe and dig through the rest of the neighbors we've mapped.